Hello again and welcome back. And we will now talk about such important relation as to signal to noise ratio, because well, the noise is very weak interference, so it can cause problems only if your signal is weak also. So it's important to know how strong is your signal in comparison to the noise level. Because if your signal is strong enough, the noise cannot do much damage to your signal and accordingly to your message symbols. However, if the noise is compared to your signal, then that's when the problems start to occur. And therefore, it's important to know how they are related to each other. So, uh, this is actually a very important parameter in communication systems, and it defines the ability of the signal to withstand this noise and how many errors it will be. It also can be used to evaluate, yes, to calculate theoretically how often you will get errors for your specified modulation type. So you will also do such calculations in your course project. So let us say you will have amplitude modulation, you will have specified signal to noise ratio, and then you will be able to tell what is the probability of an error in such a channel. And based on this error probability, you will be able to choose code for correcting these errors, because if you choose incorrect code, it can actually make things even worse. So it's important to know how often your errors are happening, and signal to noise ratio can be used to actually calculate theoretical error probability. Of course, practical values will be slightly different because of multiple factors, but nevertheless, this will be a good starting point. So, as it comes out of the definition, not definition, but like a statement of signal to noise ratio, this is ratio of signal and noise power levels. Yes, so we have power of the signal, which is represented by some signal strength indicator, yes, for short called, for example, RSSI, which is used as a as a metric in your mobile phones to show how strong is the signal, as a metric in Wi-Fi signal, how strong is your signal in percentage, like 100% or 20%. It's not really related to actual signal power, which is measured in watts, but rather than relative. Yes, it showed in percentage of how good it is. For example, you have 50% indicator, which shows that your connection, well, is tolerable, let us say so, probably. Yes. So, however, the signal to noise ratio is calculated as a ratio of two powers, of the signal power and noise power. And this noise power, I will remind you, we already discussed this, is proportional to the variance of the Gaussian process. So if we have some random normal process, we can calculate its variance, and this variance will accordingly be the power of the noise. And we'll use this approach in our practical exercise. Well, not today. Today we are going to use simple built-in function, but later on we will learn how to calculate this noise power ourselves. As for the signal power, I think there should be no problems, because you can calculate power of any signal, and basically, even in our particular case, we have even more specific signals. We have harmonic signals, which are carrier frequency signals, and well, after that, divide these two numbers each with other, and you will get signal to noise ratio. This is general definition of signal to noise ratio. For digital systems, there is another definition used, which is also a ratio. You also divide two values. Yes, the first one is the energy of one bit, And the second one is the noise spectral density. Noise density. So that is actually the spectrum which we have seen, but rather than that, the actual level. So not really like well, let's see this picture. Yes, not really like what is the spectrum value at this point or this point, but rather than this entire level is actually noise spectral density. This is the power of the noise per 1 Hertz. So 1 Hertz has this power of the noise. And not really even power, it's energy. Yes, energy of the noise in 1 Hertz frequency band. So this is the energy of 1 bit. This is the energy of noise in 1 Hertz. And these are the power. This can be easily expressed. Yes, this can be easily expressed. For example, signal power can be calculated as the energy of 1 bit multiplied, energy, so divided by symbol duration. So how long this bit is as a signal of time. So energy divided by time is the power. And noise power can be expressed as the spectral density of the noise multiplied by the frequency band. How many hertz do we have? So as you remember, hertz is 1 divided by second. So again, here we have the same measurement units, and basically this shortens out. So it turns out that these values, delta F and symbol time, can be closely related, and that will allow us to shorten them out with some specific coefficient. But let's not talk about it right now. Let us just stick to this more simpler definition, like power of the signal and power of the noise. So power of the signal can be calculated according to formulas. For example, for harmonic signal, the average power, yes, can be calculated by summing all the values of the squared voltage. So here is the square of the signal voltage. So that's why here we have 0. Yes, and it never comes below 0 because, square cannot be negative. Yes, and well, basically you just calculate the average value, like add up all the points together and divide by the number of these points. So for the continuous function, you use integral as a limit of this adding infinite number of points, yes. But under this integral, you need to remember that it's actually just a simple summation of all the values in this range and divide it by the length of the signal. Yes, so basically it can be easily calculated. Again, for real signals in practice, we have measurement units. Yes, so we have a way to measure signal power. We can use spectrum analyzer, for example, yes, to actually calculate this power. So let's return to here, for example. You can see that we have specific frequency band. So let us say now particular case 100 kilohertz. We have some level, so we multiply this level and this 100 kilohertz, and we'll get the signal power by using the tool. Yes. The only thing is that here it's expressed in decibel. Yes. Well, we'll talk about decibel as well right now. What are these decibel and why can they be useful? But before that, about the noise power. The noise power can be evaluated as a noise density and noise frequency band. Now, we already discussed that this noise band is infinite. Yeah. So instead of noise band, we take the band of our signal. because that is actually only where this noise matters. So imagine the situations. You have this noise density, which is infinite and very small. And you have some signal, which is strong, but has narrow band. So what matters the most is how much noise has gotten into our signal here. This noise can be irrelevant because we can use filters to cancel it. Yes, so, however, this part of the noise cannot be removed in any possible way and it will interfere. So that's why it's important to know this delta F of our system. How big is this frequency band? And this way we can estimate the power of the noise that is actually affecting our signal. Or it can be expressed in simulations or calculations with noise variance. Roughly it's the same, yes, so basically it's even not like 2 times or 3 times bigger, it's just this variance. This noise can also be calculated for thermal process according to this formula, where K is the Boltzmann constant from physics, yes. T capital is the temperature. So basically temperature of the element, of the receiver, of the antenna, of the component, yes, which is expressed in Kelvin grades. So basically for room temperature of 20 Celsius degrees, we'll have 290 Kelvin degrees. And B is the bandwidth, the delta F I am referring to in my course. Yes, so this comes up together here. And we can say, for example, that actually this N0 is K multiplied by temperature. And delta F is B. So the density measurement unit is watt divided by hertz. So this is power of the noise in 1 hertz. Again, and this is important only because noise can be random. Yes, so at some points noise can be very small, at some points noise can be very strong. We have average noise power level, yes, we use that, but it's important to understand that the noise sometimes can be greater than this average value. And if we have some decision threshold, yes, which tells us do we have signal or we don't have signal, and at some point noise is above this decision threshold, then our system will think that it is actually receiving some signal and will try to work with it. Of course, it will not give anything good results, but well, this will only produce some errors. Now, if we have some signal here as well, this noise will be added to this signal. That is what is causing the errors during the transmission. So usually we use logarithmic scale. So here this formula is like time. So for example, you can calculate this power like 10 at the degree of minus 2 watts. This can be calculated like 10 at the degree of minus 8 watts. Yes, and therefore after this calculation, signal to noise ratio is 1 million without dimensions. For other experiment, the signal can be much weaker, for example 10 minus 5. The noise is the same, yes, and we'll have 1000. Of course, in practice, these values are even smaller, yes, as you have seen in this picture, for example. The signal level is minus 50 decibel, which means that it's below 1 watt, yes. And basically, yes, this is actually the level of minus 50 decibel. So, the thing is that logarithmic scale allows you seeing on the same scale different numbers like 1, like 0.00000001, like million. It will be quite difficult to actually plot these points on the same plot. Well, actually, I can show you it. Yes, so if we launch Octave, let's try and plot these 3 points into one picture. Yes, so I will have some x, like first point, second point, third point. I will have some y values, so like the first y value will be 0. So I have 5 zeros. The second one will be 1, and the third one will be 1 million. Now I'm trying to plot this. Plot x, y, using red colored crosses. I will add grid lines. And what we can see here? We can see here one red cross here at 1 million. And these two crosses are literally the same. So 1 and 0.0001 are indistinguishable. Yes, and it's very hard to see that this difference is actually just as big as this. So these 2 points have been selected in such a way that the difference between these 2 levels at the y-axis here is the same as the difference here. And from this figure, we cannot really see it. We can see as if they are the same, yes? However, in reality, the difference is just as big. This one is million times greater than this. So instead of that, we are going to use logarithmic scale. So we'll plot log of y. And this way, it's possible to see this difference. Yes, we can see here. Well, the only thing is that I have taken natural logarithm, but it's not relevant. Yes, the difference is here, the same as the difference here. So if you need to compare very strong and very weak signals at the same time and see a picture them together, then a logarithmical scale is much more convenient for this purpose. Hopefully this actually shows why do we need this logarithmical scale. And well, this logarithmical scale is used very simple way. We just calculate the logarithm, decimal logarithm of the signal to noise power, and multiply it with 10. And that's how we get these decibel units. So basically, just simple calculation of logarithm without this would give you Bell measurement unit. And decibel comes by multiplying this 10, like, you know, in 1 decimeter, there are, no, I mean, like, wait a minute. 1 meter is 10 decimeter. Yes, the very same way. We multiply 10 here for the length units. And this Bell unit is actually with some history. Why it's called Bell? Well, here are some logarithm properties, like, you know, if you multiply 2 numbers, then for logarithms you can just add them up together. If you divide, you can subtract them, which is very convenient for different amplification. So imagine your first amplifier multiplies signal by 10, second multiplies by 10, third multiplies by 10, and the total amplification will be 1000. Yes, so this is very simple to calculate if we have simple numbers. Now, however, if we'll have like 1.7, if we'll have 2.3, and so on, we'll have to multiply these numbers, which is not so convenient. However, if we calculate decibels, like, for example, 11 decibels, 15 decibels, for example, it's not really important what are, then we will just have to add them up together, and these operations can be performed by engineers without even calculators. Yes, so it's much more convenient to add than to multiply. And here it comes to division and subtraction as well. So let us talk about why it's called decibel exactly. Yes, before that, let's see this small table of the sound strength. Yes, not really the communication signal, but acoustic process, acoustic wave, which also produces some pressure, yes, of the air, and therefore can be heard by us. So this value of pressure can range in very wide levels. Yes, so basically starting from the threshold of what we can hear, yes, like this 0.0002. This is the level of the sound we can barely hear, and ending with the threshold of pain. So the strength of sound is so great that it actually causes some pain. Yes, and this is sound pressure. Yes, we can also calculate sound intensity, which differs even more. Yes, this is this level, and this is this level. And Richard Graham Bell, the inventor of the telephone, was the one of the persons who was performing studies of this noise, not noise, but volume strength on the hearing of the people. Also, he founded the Association of the people with hearing problems. So he was working and studying in addition to the telephone, communications, so on, also on this topic, on the hearing of people, and was performing these measurements and so on. And he showed that this is actually logarithmic law. Yes, we can see here that with each step, we actually multiply by 10. So this is 10 times greater than this 10 times greater than this, and up to fourth to the here, which is also 10 times greater than this. And here is jet aircraft at 50 meters when it takes off, yes, which is 200 of the sound pressure or 100 of the sound intensity, which is also 10 times greater than threshold of pain. Yes, so if we need to plot all of these points on the same plot, it's much more convenient to use decibel form. Yes, this way it will be like this. So in this way, Bell just normalized them with this hearing threshold. So basically what happens is that now if we divide each of these numbers with the last one, we'll get here 1, we'll get here 10, we'll get here 100, and so on. And here it will be 1 and very many zeros. So let us calculate. So here we have 2 zeros, and here we have 9, 12, 14 zeros. 10 at degree of 14. Well, these are also numbers on logarithmical scale, and next step is just calculating logarithm, decimal logarithm. So here we'll have 14, here we'll have 2, here we'll have 1, here we'll have 0, because logarithm of 1 is 0. These are called Bell, accordingly in honor of Richard Bell, yes. And they are almost these decibel you can see here, yes. The only thing we need to do is actually multiply with this 10, which converts bells into the decibels. Deci means multiplied by 10. And that's how we got these decibels, thanks to this research of the Richard Bell. And we are using accordingly signal to noise power in this decibel also, because it's not really relevant. Here we had power of the, I don't know, of some signal, not signal, but some sound related to power of our hearing threshold, P0. Yes, so this is also a relation of two powers, just like the power of the signal related to the power of noise. In this sense, actually, noise also can be considered to be some threshold of our receiver's hearing, yes, which is called sensitivity of the receiver. And this way we compare how different is actual signal strength from this hearing threshold. Here is another scale, yes, with the same sounds. And decibel, as I've said, is a fraction. You can have more information if you follow this link also, but for now let's continue. And as I have promised, we'll compare analog communications and digital communications from the noise perspective. So imagine we have such system that sends some data in, for example, cable from transmitter to the receiver, and we use analog data signal. So here our data is continuous. Yes, so analog. The data itself is analog, because in channel we will have signal in analog form either way. Either we use digital communications or analog communications, channel signal will be analog regardless. So the data here is analog and channel is also analog. Now channel has noise, the additive, white, Gaussian noise, which we discussed already, yes. Also, there is attenuation of the signal in the channel, because when channel is propagating, or when signal is propagating, yes, from point A to point B, it loses energy. So here we have energy 1 of the signal, here we have energy 2 of the signal, and we receive the signal much weaker. This energy loss is caused by many factors, such as reflections of the signal, diffraction process, and also because when we send the signal in air, there are actually air particles which also consume part of the energy, and basically the further we send this signal, distance in meters, the weaker signal we get. And on top of that, we also have a noise. So attenuation is smaller than 1. So basically our signal is being reduced in its amplitude. And on top of that, we add the noise. So how it works? Imagine we have initially this signal, which we'd like to send. This is analog signal, yes, of some data, I don't know, maybe some voice data, for example, which is not, well, it really cannot be called data because it's not digital, it's signal, analog signal, yes, which ranges from -5 volts to +5 volts. And we'd like to send this signal in by using our communication system in channel. So what's happening is that because the receiver is some distance away, the signal is actually losing its power when transmitting. Currently, there is no noise added here, but you need to understand that signal losing power and adding noise are the processes which happen at the same time, and they cannot be really separated. We separate them here in our theoretical study, yes? Like we take one step and see what happens after step. So first step, signal loses its power and becomes weak. And that is when the noise can actually harm this signal, because for this signal, noise wasn't really something bad. We have some noise here, like this, yes. And well, this noise is insignificant compared to this signal. Now, however, after losing this power. Yes, this noise can be comparable to the signal and can change the signal. So that is what happens. Noise is very weak thing. Yes, it doesn't change signal much. For example, in this particular case, we have sent this signal not too far away and noise just added up here. Now you need to understand that from this moment on, noise cannot be separated from this signal. Yes, so basically once the signal is received, you can only see this picture, and there is no way you can see noise separately and signal separately. This noisy weak signal is all we have, and based on this noisy weak signal we have to receive information. So in our particular case, we hope to get this signal back, which then will be played by speakers, for example, and be heard by some person. So this is too weak signal to send it to speaker, so we need to amplify this signal. Unfortunately, this will amplify noise as well. So we need to compensate this loss of the signal which was caused by propagating this signal by sending it over distance. So we amplify with some amplification ratio of k more than 1. And our signal indeed is now just as strong as it was before. However, you can see that noise has been amplified as well. And you will not hear clear sound. You will hear with some static additional. However, overall it should work well, and you should be able to hear what is said, who says to you, and so on. So more or less everything seems to be good, yes. However, now imagine that we need to actually send signal much farther. For example, from United Kingdom to United States of America by using the cable which is at the bottom of the Atlantic Ocean. So this is the telephone line, yes, for calling from UK to US. Okay, so how do we do that? Because clearly we cannot send the signal all the way here and expect that it will be just as good like here. Because initially this signal will be much more weaker, yes? So this happens, for example, if we send by, I don't know, for example, 10 kilometers. After 10 kilometers, after additional 10 kilometers, it will be even smaller. Yes, so what do we do? How do we send signal on this long distance? We need to use a device called repeater. So repeater receives signal, amplifies it, and sends it further. So basically this way we can send just as far as we'd like to if we have enough of these repeaters. So yes, another important thing is that receiver has some threshold, some hearing threshold called sensitivity. Yes, so if our signal is beneath these sensitivities, the receiver will receive nothing at all. So it just will think that it is noise and will not do anything. So we cannot really afford that our signal is below this sensitivity. And for this distance, it definitely will happen, yes. So we are forced to use repeaters. Basically, repeater is this single component, which receiver also again has another transmitter, and everything is repeated again. So again channel, again receiver, again transmitter, and so on. So the repeater has receiver, amplifier, and transmitter. So we already discussed what's happening after the first transmission. So basically, let's consider that we have one repeater somewhere here at the bottom of the ocean, and it produced such a signal. It just received weak and noisy signal, which was shown here, amplified it, and now this signal is being sent further. Yes. So what will happen is that it will also get attenuated. It will decrease in its amplitude. Even more noise will come. The next repeater will amplify it, and you will see that there is even more noise now. Now, if we add third repeater, the noise increases even more. Fourth repeater adds more noise, and so on. So each repeater adds even more noise and more, and it well, eventually can become unrecoverable signal. So in order to avoid this, we need to actually prevent signal from falling too weak, like here. Yes, so we need to put repeaters more often, so the noise will not accumulate this fast. So this is for analog communications and, well, analog voice communications, phone communication in this particular case, which clearly shows the problem that we cannot get rid of this noise. We could, of course, try and use filtering to reduce noise after each stage, but it will not remove it completely. On the third, in digital communications, we can use digital signal processing, and our signal is, in this particular case, either 0 or 1. Yes, and we can always make a clean copy without a noise and send it further, because we are sure that there is only either 0 or either 1. For analog signal, there are many different values possible for signal to take, so we need to keep them all. Yes, we cannot really change them. And for digital signal, there are only two possible symbols. Yes, and it's possible to clean noise after each stage of the repeater. So how it works? So the first step is to convert our analog signal into a digital signal. As we discussed it in the last lecture, not last lecture, previous week's lecture, yes, it consists of two steps. The first step is sampling in time. So we convert this signal into timed samples, yes. So we have multiple samples here. And the second stage is quantization. Yes, we actually round the signal value to one of the, in this particular case, 8 levels. Each of these 8 levels has binary code assigned to it. We use here a so-called gray mapping. You can see that each of these each of these levels, yes, or code words for two neighbor levels is different only in one digit. So here we have 100, here we have 101. Now we compare these two, and here we have 111101. Again, only one digit difference. Here only this different, here only this different, here only this different, and so forth. Yes, so this is called a gray mapping, because it's important to, here we have rounding. Yes, we basically, for example, this point, yes, it could be converted either to this point or this point. So there is some round off error, and we'd like to produce as small error as possible if error during communication can happen. So because in these symbols also an error after we transmit data is possible. So what happens if this 110 is converted into 010? Yes, then we'll get to this point. Instead of this point, we'll receive this point. If 110 is converted, no, one error happens, yes, to 100, then, well, actually, this will happen. So in short, this minimizes the actual change because of the errors that can possibly happen in this binary code during the transmission. So we'll get as close to this original point as only possible if we use gray mapping. That's why here it's used. So, but again, now we send these binary codes as rectangular pulses. Yes, so basically, wait a minute. Understand. Need to put this. So this. Okay. So and that's what the regenerator is doing. So it receives the signal. It also amplifies it. Then it decides whether the signal is 1 or 0. So this is some sort of equivalent of repeater. However, it also performs a detection of the signal. So it makes decision, is it 1 or 0? Basically, this signal is then again retransmitted. So how it's working? Now imagine that we have this signal which needs to be sent, yes, which represents, I don't know what is here, like 1, 0, 1, and this is this sample, yes. Next will be 1, 0, 0, next will be 1, 0, 1, and so forth. So we'll send these, instead of these voltage levels, we'll send binary codes for each point, and in the same time duration, yes. And that will be our signal which we will be working with. Everything will happen the same. The signal gets attenuated, receives noise. We then get this signal at the input of the regenerator here. So that is what we have at the input of this regenerator. And regenerator amplifies this signal. Yes, so we can see that the noise was amplified as well, just as usual. But what happens then is we make a decision which of these symbols are ones and which are zeros. So this decision is made very simple way. So we basically have threshold, which in our case is 0. So if the signal is above 0, it is 1. If the signal is below 0, it is 0. Yes, and therefore we replace 1 and 0 with according voltage level. So for 1 we have 5 volts. For 0 we have minus 5 volts. This is called NRZ code. We'll talk more about different these line codes, but for now it's just to tell you that in future we'll talk about this particular assignment of the voltage levels to digital symbols. And well, yes. So what happens? This clears all this noise. So basically we remove this noise by making decision. Yes, so this is 1, this is 0, this is 1, this is 0, and we send further this clean version. Now it's understandable that we can repeat this process as many times as we'd like, and in the end we'll still get this clear signal. And well, that's actually how digital communications are superior to analog communications, because we can well, in theory we can eradicate noise completely. Now it's not really practical always, yes, because it has some requirements for coding, but at least theoretically for digital communications it is possible to send without errors at all. And Shannon was the first scientist who proved this. Yes, he proved it mathematically, meaning that he had theorem which he has proof for, and well, this showed that actually it is possible to transmit data without errors if we use digital communications, if we use special coding. And this is good news, yes, because before Shannon it was considered that it is completely impossible to send data without errors, just by the nature. Yes. However, it turns out that if certain conditions are met, it is possible even to have 0 errors at all. So we'll talk also about more advanced modulation types, literally, which is called one of them CAM16, quadrature amplitude modulation. Basically, this CAM16 has not 2, but 16 different signals. So here we had only 2 signals, 1 and 0. Yes, for CAM16, we have 16 combinations of 1s and 0s. So starting with 4 zeros, ending with 4 1s. Yes, and each of these symbols has different amplitude in 2 axes. So, for example, this point, yes, sorry, this point. I will also draw axis. Here we have axis. So this point has amplitude on the x-axis -3 and amplitude on the y-axis +3. This has +3 on both axes. This has +3, -3, and so forth. Yes, so on each axis we have 4 different voltage levels. So we have -3, -1, +1, or +3. For x-axis, 1 signal. For y-axis, the second signal. Yes, and basically then we combine these 2 signals together. Now I don't want to be too technical about it. There just is some way of merging them together in a complex plane, for example. Yes, and then we send this data. So original signals are just points inside these round shapes. Yes, so these are original symbols. Now, because of the noise, what we receive can be a little bit different. So our original signal, and we receive different fluctuations from this original point depending on the noise power. So here we have 1 signal to noise ratios, here we have different signal to noise ratio, and here even different. So you can see that we go further and further from this center as the noise becomes stronger. So yes, and we have SNR1 is maximum, SNR2 is in the middle, and signal to noise ratio 3 is the worst of them, meaning that the noise is the strongest and the signal is the weakest for this picture, and vice versa. Here we have the strongest signal and the weakest noise. So this clearly illustrates this process of making, and the error happens when we have sent this signal, and because of the noise it happens to be here and is closer to this point. Yes, and that's how the error happens. And clearly, the more noise we have, the more often such situation will happen, and the worse will be situation. So what is BER? BER is bit error rate, so the probability of error. So for this signal of noise ratio, we have 1 error in 100,000 symbols. Yes, basically. So 1 per 100,000. Here we have 3 errors per 1,000 symbols. Here we have almost 2 errors per 100 symbols. Yes, so you can see that the probability of error increases because SNR increases. Also, there exist some formulas which you can use to put inside this SNR into the formula and get this error probability without even making simulations or practical experiments. Yes, without needing to send all this data to receive it, to see where goes each data point, and so on and so on. So we'll also do this in your course project. We'll actually make simulation, but not for quadrature amplitude modulation, for simpler cases. And furthermore, we will also add coding to here to see if the code can actually help us and improve the situation, because these pictures show you no coding. Yes, no coding here is used to correct any errors. Alternatively, we can add a code and these values can be improved, and this also. So yes, so basically for today's lecture, that will be it. If you have any questions, please ask them. I'm here and happy to answer. Also, we'll have practical exercise, and if you think of more questions, by that time you can also at the beginning of the practical exercise ask them too. But for now, I think we can conclude our lecture and then have a break of, well, maybe again of around 15 minutes, just to start at the correct time. We'll start at 10:45. Yes. So we'll start at 10:45. Please see if you have Octave installed in this meantime. We'll use Octave if you'd like to follow up and do everything at the same time I do. But if you haven't yet or cannot install it yet, don't worry. I will upload these videos this day, or maybe, yes, this evening. Yes, you will have all the videos available, so you will be able to play back, repeat all the parts of the exercise, and go into the speed which is comfortable for you. So thank you for attention and see you again in 15 minutes. We'll do practical exercise.